I'm really going to talk about words, okay? Because most of you, although everybody can read everything on that screen, I'm not sure we all have a common understanding of what the words on demand mean in the context of energy, what the word sustainable means in context of energy, even what the word energy really means. Okay? And I will try to use a technical definition of energy. Surprise, surprise, right? Certainly, I would guess most of you really don't have a full appreciation for the role of energy storage in the issues related to energy and sustainable energy and how we use it in our society. So my objective is sort of to have you understand the objectives of these words. So at the end of the presentation, if I haven't been successful at doing that, you know, we've had something less than an optimal day. Just so you know, Murphy helped me do this presentation. It was on my memory stick that got fried last Thursday night. So this presentation was put together since actually Sunday because I was tied up until Sunday afternoon. At any rate, so there we go. And you see, technology doesn't want to work again. So let's see if the computer works, right? Okay. What I really want to talk about is the operational definition of sustainable and what that really means in sustainability. I'm going to talk about energy in some of its forms, which I've already sort of briefed you on with the cheat sheet. Okay? I'm going to talk about two very familiar examples of on-demand energy systems so that you can have some appreciation of that and relate it to your own personal life, hopefully. Okay? I'm going to talk about the why of energy storage. Why would we even think about storing energy? I'm going to talk about over-the-road refrigeration and thermal storage, and that's sort of what led to this lecture. Is I had a research contract where we had to worry about trying to replace over-the-road refrigeration equipment with thermal storage equipment, and I got asked if I would do a presentation on that, and I didn't. I made the executive decision. I didn't want to put you all to sleep, so you're going to only get 3 or 4 slides about that. So it's a really brief summary. E.g., I'm not going to go through all of the design work and the model work and all that stuff related to that. And then we'll conclude with a single slide. Is there some magic thing? It'd be nice to. Oh, there. I figured out how to work it, right? Here's the definition of sustainability. And this is not unique to me. If you read books about sustainability, which I do, and I study sustainability, I do research in the sustainability areas, it is really the intersection of 3 things. It's the intersection of energy, environment, and economics, represented here by 3 different colored circles, energy being the red one, economics the green, and blue represents the environment. Over here on the side, there are some ifs about this. Okay? It's sustainable if you have the energy technology. If you don't have the energy technology, you can't build it. So it's clearly not going to be a sustainable solution. Okay? It's sustainable if the environmental laws are satisfied. If they're not satisfied, guess what? You're not going to be allowed to build it either, and so you can't use that solution set. Okay? And that's an important thing for you to remember, because it's the laws, and they change along with the technology, that really control what's sustainable. Okay? The last thing are the economics, and if the economic return of investment is not adequate, you're not going to be able to attract investors to build the facility and build your project. Okay? And so the reality is that if the energy constraints and the environmental constraints and the economic constraints are not all met, it's not going to contribute anything to the supply of energy. Okay? So graphically, of course, it's represented by a small subset, and believe me, if you're in the design business, you discover just how small that subset is. It's a pretty small subset of all of those choices. What's entertaining about the energy business is that that subset changes continuously. It changes continuously because the technology of energy, the environmental legal constraints, and the economic return on investment constraints change all the time. So you really have to be careful when you do a startup on a company, you know, to try to project what's going to happen to some of those issues during the startup time. Okay? Alrighty. So this is probably the most boring slide here, but it's a necessary evil, otherwise we're going to have a hard time even discussing the subject with one another. Energy is the ability of a body or a system to do work. And by that we mean, in essence, lift a weight or cause a weight to be lifted. Okay? So if you can convert it to work, you're in good shape. Okay? Heat is the transfer of energy. What's interesting about energy, like this little controller I'm holding in my hand, has energy. It has energy stored in it. Okay? The only way you can tell there's energy in it is if you transfer energy from it to something else. Okay? There's two ways of transferring that energy that are common. There's lots of mechanisms, but at the end of the day, heat is the transfer of energy from something, from one body to another, by virtue of their temperature difference. Now, if I asked you, is it possible to transfer heat from a high temperature source to a low temperature source, you'd all tell me yes. Okay? Is it possible to transfer heat naturally from a low temperature source to a high temperature source? That does not occur naturally, right? We all know that. That, folks, is a very brief statement of the second law of thermodynamics, which, by the way, was discovered before the first law was. Okay? Just to let you know, okay? Work is the transfer of energy from one body to another, okay, by the virtue of a force field interaction, okay? And I've given you an example for that because the idea of a force field might be hard for you to accept. So I said if you've got moving air against a turbine blade like you have on top of a windmill, okay, or on top of a wind turbine, okay, the air's interaction with the wind turbine blade is a force field. It's a pressure field against the blade. It actually turns the blade, okay? And so it's an imparting, and it's a change of energy in the airstream, and it gets imparted to the turbine blade. Okay? A cyclical engine is the last piece of this little definition puzzle that I really have to cover with you. And so it operates in a cycle. An engine is a device that takes heat, converts it into work, and it does so in a cycle. And by that, I mean the cycle repeats in time. A good example of that is your automotive engine that you have in your car, where the piston goes up and down, and depending on whether it's a diesel or a regular Otto cycle internal combustion engine, it might go up and down twice. But it repeats. It goes through a cycle set point in time. Those four words are extremely important to you. Okay? All right, so let's see here. Okay. Now I had to define those in order to do this slide, so this is the second boring slide. Okay? All cyclical systems producing work, biological and man-made, share the following. Okay? They all buy and consume energy, okay? Somehow they get their food and they get their fuel. Okay? A tree is a cyclical engine, sometimes with a very long half-life, but nonetheless. Okay? Clearly, your automobile is a cyclical engine, and clearly, when you run your automobile, you're the consumer. You buy the energy, you put it into it, and you get the work out of it. Right? They produce work when demanded by the system that they serve. Okay? And so what that means is that when you demand more energy out of your car and you push down that gas pedal, you provide it more fuel and it produces more work, it goes faster. Okay? They produce waste heat. That, folks, is what the radiator is on the front end of your car. It gets rid of the waste heat. Okay? The system efficiency is defined as the work produced by the cyclical engine divided by what you paid for, e.g. the cost of the fuel coming into it. Okay? They also produce other wastes, gaseous, liquid, and solid. They can produce one or more of those forms, or all of those forms. Okay? So it's one of the interesting things about this is you'll notice that it is impossible, according to the second law of thermodynamics, that all of the fuel that you put in gets converted entirely to work. You always have to produce waste heat. Now you say, that's interesting. So let's bring it a little closer to home. So I want us to analyze what happens to Susie and Ahmed. Okay? Two human beings. Okay, is this close enough to home for us? Okay? Their bodies, whoops, I'm sorry, I'll get this straightened around. Their bodies are cyclical chemical engines. I went the wrong way. Their bodies are cyclical chemical engines, and we operate at 98.6 degrees Fahrenheit. In fact, the human body is a very fascinating cyclical chemical engine. It's got all sorts of interesting protection mechanisms built in, one of them being that we protect this 98.6 Fahrenheit a lot. I mean, the body's mechanisms for doing that are substantial. Intake. Every day, you know, we get up and we eat our bowl of Cheerios or whatever, and we have our lunch and we have our dinner, or in some cases we'll eat 2 meals, some places 3, other people eat every other hour, you know, who knows, okay? All right? We eat on demand. We eat when we are hungry. We demand that that food be there, okay? And if we get hungry enough, we become very demanding about that food being there, okay? So we count on a whole bunch of systems to provide us that food every day. Okay? Even though it doesn't deliver much energy per buck, as you already know from your cheat sheet. Okay? Your body counts on that, and you are an on-demand energy system. Your body is. Okay? We all do mechanical work. You know, it all took effort to walk up the stairs today. It took effort to carry your book bag around or your briefcase or whatever. That's mechanical work, and we all do mechanical work every day. Okay? In addition to that, every day, you transfer a portion of the energy consumed to the environment. You have to do that because your body is a cyclical chemical engine. It doesn't have a piston going up and down in it, but it does process the fuel that you consume as food. Okay? The human body, however, is quite inefficient. If you calculate your thermodynamic efficiency, it's only like 2 or 3%. Now, one of the things that's interesting about it is in the summertime, okay, where the air temperature is 70 degrees Fahrenheit, your efficiency goes down. Okay? And if it weren't for the other mechanisms built into your body, it would really go down a lot. But in fact, in the summer, what happens when you do a lot of work? You sweat. And the evaporation of that water off of your surface, okay, is how you are rejecting the heat, okay? And it's, by the way, what maintains the 98.6 Fahrenheit. Okay. In addition to that, of course, your bodies produce waste, gaseous, liquid, and solid, okay? In addition to food, however, Ahmed and Susie demand electricity. How upset do we all get when there's a blackout? Okay? And we've all experienced various and sundry ways of blackouts, some of them minor, some not so minor.
Excuse me, I have a question.
Yeah.
How do you calculate the 2% efficiency?
It's the thermodynamic Carnot temperature ratio, which is just the high temperature, the body's temperature, minus the environmental temperature, divided by the body temperature in absolute temperature. So it's pretty low. And in fact, now that you've asked that question, that was a setup. See? Now that you've asked that question, the closer the body temperature is to the environmental temperature, the less work you can get out of the energy source. So while the amount of solar energy falling on the face of the Earth is several hundred times, 200 times more than what humankind consumes, okay, the problem is it's falling on the surface of the Earth at or close to the environmental temperature, so the amount of work that you can get out of it is very small. Okay? So it was sort of a setup. Thanks, Narayan, for asking the question. Okay. All right. This is a photograph of a typical power plant. Now, I randomly chose this from the web. Okay, you can go out and find all sorts of photographs. This one turns out to be pretty good from a lot of perspectives. I just want to point out to you some things about it. First of all, when you see these, you know, a lot of people driving down the road will see cooling towers, and that's what these are. These are cooling towers. Okay. They'll say, oh, it's a nuclear plant. Well, not true. It's just a way of removing the waste heat from that power plant. That power plant can be a gas plant, it can be a coal plant, it can be a nuclear plant, it can be actually a solar thermal plant. Okay? So they're cooling towers. I'm not going to explain to you how a cooling tower works except to just point out to you that what's coming off the top is the water that's evaporated, okay, which actually carries with it the waste heat from the plant. So it's water vapor that's put back into the atmosphere. The gaseous waste that's produced by the power plant is here at the top of this stack, and after, I will tell you, there's great pains taken to remove most of the pollutants from that stream. And so by and large, what you see coming off of a coal-fired, even a coal-fired plant like this one is in fact water vapor there as well from the combustion process of the coal. You can tell it's a coal plant, and you can tell it's a coal plant here because the transportation mechanism, which is a belt that connects the coal pile to the boiler, which is, the boiler is located in these big block boxes here. And the boxes are actually just built around the boilers themselves. Okay. They're actually, portions of them are the outside of the actual physical boiler. At any rate, so the coal is provided to those boilers through that mechanism. You can tell those are the boilers because these are the steam lines coming off of the boilers. Okay. So if you know anything about power plants, you say, aha, that's a typical coal-fired power plant. Okay. Did you? Okay. We ready to move on? Okay. Power plants. Now, so what I'm going to do now is compare a power plant to Ahmed and Susie. Okay. A power plant is a cyclical chemical engine, much like Susie and Ahmed. Okay. The difference is they operate between 800 degrees Fahrenheit and 1500 Fahrenheit. Okay. They don't operate at 98.6. They operate a long ways from the environmental temperature. Okay. Long enough so, in fact, the seasonal variations of temperature of the environmental temperature have little impact on their efficiency. It has a minor one, but it's very small. Okay. Their intake is a fuel, and the fuel can be, if it's a conventional power plant, gas, natural gas, coal, okay, or nuclear, okay, or coal and natural gas, because they're running two different cycles within the plant, and that's called a combined cycle plant, okay, which you'll see in a little bit. They do mechanical work. The mechanical work they do is they end up turning the shaft of the generator that generates the electricity that comes out of this wall. Okay? How it gets there, you're going to see that too in a second, how it gets there. But at the end of the day, they turn a mechanical shaft that turns the generator and makes the electricity. They're quite efficient at producing work compared with Ahmed and Susie. Okay? Okay. Ahmed and Susie, remember, with 2 to 3%. Typically, power plants have efficiencies varying from 30% to almost 48%. Okay. And they produce waste, gaseous, liquid, and solid, and depending on the fuel that's used, you can get all three of those. Typically, you get just solid fuel, solid wastes, and gaseous wastes. Okay. Oops, I don't have to go up there.
I had a quick question.
Yep.
Because of the high temperatures that they operate on, the weather patterns don't make a difference?
That's right. The environmental whether the environmental temperature is 90 degrees Fahrenheit outside or 20 below, that would change the efficiency of the plant, okay, a little bit, okay, because you can't freeze the water, so they have to keep it above like 50 degrees Fahrenheit is the low temperature. But the temperature at the bottom doesn't change much. It might go from 50 to 70, and that's about all. So in terms of changing the efficiency, it really has a minor impact. What does control it is the high temperature, which is a materials problem. The only reason we can't make more efficient power plants is because of the material science involved in making particularly the turbines. Okay. All righty. Now I want to talk to you. Now we've got the power generator, right? So we're at the aft end of the generator, and the plant is producing power. The power plant has to connect to you and me and our homes and our computers on our screens, and so it has to come out of that wall socket. Okay. In order to do that, there is a vast network of wires in the country, okay, that connect the small number of power plants in the country to the millions of users. Okay. The country is broken up into sections. Okay. Sometimes they're along state lines. Other times some states have multiple grids within them. Okay. You're going to see both examples here. The first is New York State has one grid operator, and the name of the New York State grid operator is NYSO. And they are responsible for controlling and taking all of the energy sources from the few power plants that we have and distributing it to the however many people live here, 15 or 18 million people in New York. I don't know what the current population is. And so what I tried to do here is to give you some sense of that. Because we have something like 100 to 200 power plants, and typically the area of this circle is tens of millions of people. Typically it's 10 to 20 million people. And so you're connecting a few hundred points with 20 million users, all of whom are Susie and Ahmed, all of whom have the right to go over and turn the switch on or turn it off, plug in their computer, start up the hair dryer, turn on the washing machine, turn on the electric stove, whatever, okay? And they do that entirely at their will. They are all 15 million of those people that are in the grid are on-demand customers that are not controlled by anybody. Okay? So if you put yourself in the position of the grid operator, NYSO in our particular case, they take great pains to make sure those 15 million people have that electricity every day. Okay? And you will see that because some of those folks are named reliability councils. Okay? Not in New York State, but in another state that I'm going to talk about in a minute, which is Texas. Okay? And the reason for that is they are responsible for providing you reliable power. So part of the capital investment is down here in the power plants. The other major portion of the capital investment is tied up in the grid. Now we all know about the grid, right? Because we have major power lines running through the Mohawk Valley that connect the St. Lawrence Seaway and the nuclear plants to New York City. And they all go through Clark Energy Center up here, which handles about 1/3 of the power of the state of New York. Okay? And in fact, there was a huge political brouhaha because they didn't want to produce additional power lines going from those resources to New York City through our region. Okay? And I don't want to get involved in that political discussion, but the reality is that, you know, if there's a bigger demand for electricity, NYSO has to figure out how to get there. Yes, Will?
Dr. Somerville, I've read in a not-so-great magazine that algorithm that's used to distribute the power is along the lines of something like linear programming.
It is. It is.
It is? It
is. And wait till you see the rest of the story. It is. And the answer to the question is it is extremely complex.
Thank you.
Okay? I think that's a fair statement. It's extremely complex. Okay. The grid and its operators who connect all of those people together manage the variation in the cumulative electric demand second by second. Okay, they control the frequency, they control the voltage, they control the current that's delivered. They control all three of those things to ensure they're within spec, so that your clocks keep time, so that you can use your computers without worrying about them burning up. Okay, and they do that while meeting the economic and environmental constraints for the power generators, okay, as well as the endpoint customer. So to tell you that it's a complex algorithm is the understatement of the year. Okay. Okay. How complex is it? Okay. Now I've switched gears. I've gone from New York State to Texas with this chart. And the reason that I'm using Texas is that the strategies for meeting reduction of CO2 production in the state has changed dramatically from Texas, where what we're doing is we're shutting off the plants in New York City that are gas-powered plants, okay, which are the lowest polluters, by the way, and drawing on our assets in the nuclear plants, which are no CO2 production, and in St. Lawrence Seaway hydro plants, which are also no CO2. Okay? Got it? But in order to do that, what do they have to have? A way of getting the power from the St. Lawrence Seaway and the nuke plants to New York City. Okay? So, their power curve and our power curve looks the same. This is what the diurnal power curve looks like in a typical grid. Okay? And so, you know, it starts out here, this line is midnight, so each line represents midnight between the 2 days. Okay? And you go from, you start out in the early morning, okay, and then everybody starts getting up, they turn on their toasters and they make breakfast, and they go about their day, they get to the office, they start up their plants, we start up the manufacturing plants that use electricity, all of those things that we do to make a living and to have our country be an economic success that use electricity, which, by the way, is about 1/4 of the total energy use of the country. But what's important about that statement is it's pure work. And then it reaches a peak here at the end of the day, you know, you come home, okay, and this peak is also caused by the air conditioning load, especially when you're in Texas. Well, actually even here, okay. And you'll notice this is actual data from July 12th of 2009. Okay. And then what happens is, you know, the air conditioning load goes down, the plants shut down, they tend to shut down, but at least some of them do. The companies close down and people come home and they go to bed and they go to sleep, and the cycle sort of repeats. Okay? So that's how the global cycle happens. Okay? Now, what's interesting about this slide is they have shown you how they get the power, where the power came from, what fuel sector the power came from. Okay? And the fuel sectors that are covered are nuclear, coal, combined cycle. That's where you have a combined coal plant and a gas plant. A gas steam plant, which is just a regular power plant run by gas, private gas and gas turbines. These two over here are actually gas turbine plants. Okay? And then wind and other. The other in this particular case is solar photovoltaic and geothermal. Geothermal is different than the others because geothermal is an on-demand power plant, just like nuclear, coal, combined cycle, gas steam, private gas, and gas turbine are. Okay? The solar photovoltaic is that the energy storage required to meet the power demand from a stochastic source doesn't exist. We don't have good commercial scale energy storage. And this graph shows you how much you need of that to do that, which is substantial. Okay. On top of that, I'm going to say one other thing about this graph and then move on. If you're in the business of paying off the debt on the capital investment for the power plants, and it doesn't matter whether it's wind, solar, PV, or gas, or coal, or nuclear, okay, It is in your interest to have a nice level curve across here. So you have a predictable result, right? Okay? The last thing in the world you want somebody to do to you is start messing around with how much power you can produce. In order for the stochastic sources, what they call in the business unreliable sources, I call them reliable, we just don't know how much and when, okay? They are dipping in and they count on the stochastic sources, the wind and the solar PV, count on, they must have all of these other sources in order to make the pieces fit. Okay? Now, this graph gives you a comparison of what happens between the capital investment in the plant and the cash flow in the plant that supports the capital investment by fuel type. Okay? On the left, you have what's called generation capacity. Capacity means if I build a 300 megawatt power plant, I own a 300 megawatt power plant. If I buy a 3 megawatt wind turbine mounted on top of a 120 meter pole, okay, and stick it up there, that's the size of a bus, by the way, of a regular bus that you see driving down the road, okay, 100 meters off the ground or so. The bottom line is that's the capacity of that facility, okay? So that's what capacity means, and it's what you pay for with your capital money. So when you see the word capacity, it means this is how much we have in installed capacity, meaning this is how much energy we can generate. Okay? The generation, though, is when I sell the electricity, okay, and it goes down the line, I get a cash flow fed back into my facility for doing that, and I sell it by the amount of energy I produce, which is kilowatt hours. Well, that's not the only parameter, but that's good enough for this discussion, okay? So at the end of the day here, the constraints that ERCOT, in this case, ERCOT is the Texas Reliability Council. It stands for the Reliability Council of Texas. That's what ERCOT stands for. They, just like New York ISO, are responsible for managing what fraction of the time we get energy out of the natural gas, what fraction of the time we get out of coal and out of nuclear and out of wind. We have relatively little wind in spite of the fact that we have several wind farms around here. In terms of the total grid operation, it's not even close to Texas. Texas has a very different strategy. Their strategy, by the way, is to develop the non-carbon, the zero-carbon resources. Okay? That's their strategy at meeting the EPA's requirements of reducing CO2 production. Okay? All right? So they are investing enormously in wind and solar PV. So this shows you, for example, if you look at nuclear, that they've got 6% of the generation, okay, the capacity, but they are selling 14% of the revenue stream. So they're getting 14% of the revenue stream for only 6% of the capacity that they have installed. Coal has 16%, okay, of the installed capacity, and they're selling 37% in spite of the fact that they have a reduction of CO2. Because why? They're worried about the price that the customer pays. So like if you look at New York's kilowatt hour rate, Texas's New York rates versus Texas's electric rate versus New York's, you discover that Texas is about 70% of that in Texas, of New York. So they're much cheaper. Okay, but at any rate, so they control what fraction of the power comes from coal, and they control what fraction comes from natural gas, all to reduce the amount of carbon that they're actually producing. That's only one of their constraints. The other constraint is they've got to make the return on investment for all of these resources so people stay in business. They've got to make the economics work for the state so that they can attract more industries to their state and have lower cost electricity. And they just have to manage a few million miles of power line in the process, along with the 200 odd companies that are putting electricity into it. So what, yes, William, it's a linear programming problem of the first order.
Thank you.
Okay? Does that help understand?
It does.
Okay. All righty, so stochastic energy sources and commercial scale storage. Renewable sources really can't be controlled except you can dump the power. So, and in fact, a wind turbine has a cutoff velocity and a startup velocity, and you simply won't see them. So if the wind is below a certain velocity, it won't run because it's not worth running the turbine. Okay? And if it's above a certain velocity, you actually feather it out and lock the blades with feathered and turn it into the wind so that you won't ruin the turbine. Okay? So the facts are that in between those two range, you'll run the turbine. Okay? But if the grid doesn't need the electricity, they'll call you up and say, hey, shut off your turbines, and in which case you feather them and lock them. Okay? So that's the degree to which the control exists for a wind turbine, or at least in the global sense. All of the stochastic sources can contribute to the reduction of CO2, which is an important constraint. They can also all contribute to the electrical demand. It's just that they cannot be counted on meeting the on-demand needs of the grid. They can't at the present time. What's missing? Well, the answer is energy storage. And today, the societal power demand requires both the traditional and the stochastic sources. And we absolutely have to find a better way at solving the commercial scale storage problem. Okay? Which is how I got into this research project to begin with, because we were working on energy storage issues. Okay? So here is one solution that some of you may have seen. It is a commercial scale compressed air storage for offshore wind farms. Okay? And what it is it's a great big huge balloon. Okay? It's fastened to the ocean floor. Okay? And typically at something like 300 or 400 feet, or maybe 500 feet, so it will take several atmospheres of air pressure. The way it works is pretty simple. They fire up their wind turbines, okay, which if they're placed appropriately offshore, they tend to blow most of the time. And what they do is they generate electricity, and they take that electricity and they run great big huge air compressors. And those air compressors blow up the balloons. And they store energy under the ocean floor, okay? And they use the weight of the water above them to maintain that pressure, okay? So they now have stored mechanical or stored air there. And then when they need to provide electricity to the grid, they run the air through an air turbine, which turns the generator, which they sell into the grid on demand. Okay? All right, and the efficiency of this system, I think the best they've done so far is 85%, which is pretty good. So they're taking a 15% penalty for storing the energy. That's way better than batteries. In fact, the problem with batteries is you can't really build a battery that stores it. Yes, you can use, there are other storage mechanisms. I'm not going to talk about hydrogen, but that's one of them. As long as you're willing to live with hydrogen. How am I doing? Okay. Okay, 3 more slides, all right. This is how the whole thing started, right? How many of you have seen a truck like this? Okay, all right. Running down the road, and they're the refrigerated trucks. If you stopped on the interstate during the summer, you can hear all the refrigerated trucks running, right? Because the reefers will be all running. The reefer is the refrigeration unit. Well, the trucks themselves are called reefers because they're pulling a refrigerated trailer. The refrigeration unit, and this one is hidden. This was such a nice clean truck, I had to show it to you, right? At any rate, this unit is hidden back here. A typical reefer, okay? A typical reefer has a weight of 3,000 pounds. That's how much the refrigeration unit on the front of that trailer truck weighs. Okay? It consists of, at the minimum, a 100 horsepower diesel engine, a 4-cylinder refrigeration cycle, all of the controls, the heat exchanging equipment that are required to run the refrigeration unit, okay, and a connection to the inside the trailer truck box, okay, to actually condition the space, and the space is usually conditioned between 0 and 45 degrees Fahrenheit depending on the product load. Okay, so they weigh 3,000 pounds. Okay, the constraints for building the storage system was that we have to be able to maintain the box at the same conditions the reefer maintains it at for a period of 24 hours at 0 degrees Fahrenheit when the air outside the box is at 95 degrees Fahrenheit and 95% relative humidity. Okay? Now that's just the constraints, right? I mean, that's one of the constraints. So if you're going to build a thermal storage system that replaces the reefer, it's got to weigh less than the 3,000 pounds that the reefer weighs. Okay? It's got to be able to do the same thing as the reefer does, okay, for at least 24 hours. Okay? It's got to be able to be swapped out depleted storage units with charge units in 30 minutes. That was one of the initial conditions, because the idea is that you can build storage, you can build places on the interstate where if you're running out of storage, you can pull in, replace your storage unit, and go on your way, fill with diesel fuel, eat your lunch, and be gone, right? Okay? The transported product has to remain safe in the event of a leak. Okay? It's got to be capable of being charged by the traditional onboard reefer, and this constraint came about because the strategy is that nobody is going to take a refrigerated truck with $400,000 or $500,000 worth of product and put a thermal storage unit on it without knowing for sure that it's going to work. And so they've said, well, you got to go through a substantial proof of principle testing here in order to make this work. Okay. The charge, however, really changes because now you can actually charge these units with an efficient dual-stage refrigeration cycle versus the single-stage refrigeration that's used in a reefer. Okay? And the efficiency is substantial. It's a 3-fold increase in efficiency. Okay? At the end of the day, they wanted to do it under 2 hours. Now, that gives you a really interesting heat transfer problem. In fact, the set of constraints on this are entertaining. Okay? Ryan, I see Ryan back there, and he's working with or for New West on this project, so he's somewhat familiar with it. So we are working with New West Technologies to develop a proposed design. I got involved with the project because one of our former students called me up and said, hey, it looks like an interesting project, but I don't know how to do all of it. Will you work with us? So that's how I got involved. NYSERDA's interest is, NYSERDA's board is run by a group of electrical executives. They want to fill those valleys that you saw on the power curve. And they see this as an opportunity to do the charging of the thermal storage units, okay, off-peak, when they can build a better return on their investment. So they have some purposeful or some interest in doing that. I'm going to show you this one curve. In essence, once you get a design for a thermal storage unit, okay, and this is the simplest thermal storage unit as we could conceive of. It consists basically of a set of tubes. The tubes have fins on them to enhance the heat transfer, and it's with a phase change material. In this particular case, it's ethylene glycol and water, so that you can actually control the temperature at which the mixture freezes, okay, so that you can vary that actually, and you can actually have thermal storage units that freeze at different temperature levels, so it had all sorts of advantages. Also has some really interesting technical challenges. There's about a 25 or 30, how many parameters did you count them in the model? But there's 25 or 30 parameters in the model. So I'm not going to put you all to sleep by going through the detailed analysis of this. At the end of the day, if you put fins on the tubes and you do it correctly, okay, you can get a substantially enhanced heat transfer rate versus a plain tube. Okay, The amount of energy that's stored in the device is the interval, is the area under this curve. Okay, and that's why the curve fit data are given there so that you can actually calculate how much energy this unit stores. Okay. Okay. Then I think the conclusions are that sustainable systems are going to be around with us for some time to come. At least using the word sustainable as I've defined it here for you. In fact, that's the big issue, is sustainable is often confused with renewable. The two are very different. Okay? A renewable energy source is one simply that uses the stochastic resources of the atmosphere, whether it be wind or the sun. Okay? Whereas a sustainable system has to meet all of the constraints. They've got to meet the available energy technology, the available law, the environmental law, and the economics return on investment. The renewable resources, okay, will be part of the solution. They are stochastic in nature. They require commercial scale storage to meet on-demand needs of people. And that's a huge research area that you're going to see more and more people investing in. The research is continuing. It's been ongoing for some time. I actually started doing storage research in 1973, so you can take it from there. It's not going to stop right away. Thermal storage to replace reefers and over-the-road refrigerated vehicles appears possible, represents a good research area. I promised you that we'd be out by 1 or 1:15. It's 1:05, so. Are there any questions? Yeah.
Just going back on what you were talking about before, how the New York State grid system has to monitor how much electricity is sent back and forth from point A to point B. I know during the summer living upstate New York, we sometimes get an alert saying, lower down your energy consumption. Because
SUNY gets that all the time. SUNY IT.
Yeah, right.
We're on a load shedding
Gotcha.
rate structure.
Okay. My question was, if demand that we put on the system can't be, what's the word I'm looking for? Managed, how are we asked to cut back to give forward?
The electric companies are managing loads two ways. One of them is with their major customers like SUNY IT, and if you're a big company, that's one of the things you do, is you actually agree to manage load by shutting off your major demand for a portion of the day, because it gives you reduced electrical rates. Okay. The other way is it's coming to your local friendly consumer, and they're called smart meters. And for example, in ERCOT, they already have installed over 13 million smart meters. Okay, so they're actually controlling how much electricity your major appliances use, and they'll shut off your air conditioner for 5 minutes and then turn it back on. They'll shut off your water heaters if you have electric water heaters. They'll shut off your major electrical demands with a smart meter, and then turn it back on. They try to choose relatively static devices that you won't miss. So if somebody shuts off your air conditioning for 5 or 10 minutes, you're probably not going to miss that, as long as you get back on at the end of the 5 or 10 minute period of time. So that's how the utility grids in the country are trying to manage the load end of the piece of the puzzle. Okay. Any other questions? Well,
Dr. Somerville, I know you've been interested in students' welfare for a long time. Taking what you just told us, when we're advising students in terms of career fields, what's the takeaway from this in terms of the students, please?
If I were a student looking for a long-term stable industry to work in, I do not believe electricity is going to go away. So I would tell you that any company that makes equipment and sells it into the markets related to electrical generation production, or the utilities that are involved with both making the electricity and the grid operators who are responsible for distributing it, are going to be around a very long time. I do not see a replacement for electricity coming onto the market that's another work form that's going to replace electricity. I don't believe that will happen, certainly not in my lifetime. Now that I've said that, I'll probably be wrong. So I would say any industry related to that is A, stable, and B, the bad news of the day is it's controlled by the public utilities, which means they don't make as much money as some of the other private firms. But for example, if you, if we go back and we look at this, okay, this is innovative energy storage. It's being successful. Our friends in Canada started it, actually.
Thank you.
So it's a fun company to work for. They're probably going to make money off of it. In fact, they are making money, so. Any other questions? Well, if not, thanks for your time. We got you out of here. Good.